All right, it's a pretty good crowd. Thanks everyone for joining. I'm just gonna get started. I think, well, Timur Dumler last year has been giving this talk, and I think he states the C++ safety question pretty well at the end of his talk. It says, does a subset of a superset of C++ exist that achieves similar safety guarantees to Rust, is useful and expressive enough, and is compatible with today's C++? He says nobody knows, but I think the answer was always obviously yes. We can extend the language and build in the missing infrastructure. The real question was like, was anyone mad enough to do it? And you're going to see that we have an answer to that now. To make a safe language, you have to do more than just turn off potentially unsafe features. A lot of the features are banned in the safe context, like you can't dereference raw pointers, or you can't access mutable global variables because of thread safety. If we turned off all the things that can be used and produce unsound code, we wouldn't have an expressive language. So you have to come up with alternatives. And I've kind of broken down the memory safety space to these 5 domains. So the first and the hardest problem is lifetime safety. How do you avoid use after free or dangling pointer bugs? And the answer that Rust gives is borrow checking. The answer that Java and C# give are garbage collection, and other languages like Swift use automatic reference counting, which is morally the same as garbage collection. But in C++, we have manual memory management, and we want to be able to deal with references to objects that are allocated on the stack and not just on the heap. So we need something like borrow checking, which works at compile time and doesn't really change the meaning or the execution of our code. It just checks that it's correct. Another issue is the null pointer variety of type safety. If you look at something like std unique pointer, it has a default value of 0. You can default construct it, and then if you use the star operator or the arrow, you get undefined behavior, because that will produce something that's morally equivalent to a null pointer dereference. And that's bad. And the way to get around that is to create types that don't have defaults. So we want to have a unique pointer that has no default state. And that means that std move won't work because there's no way to clear out the old value. So we need an object model that supports relocation. The other variety of type safety that we have a real solution for is dealing with things that are like unions. And in C++, that would include std optional and std expected. Both of those exhibit undefined behavior if you use star. If you have a std optional, it's not engaged, so has value is false, and you star it, well, that's undefined behavior. And that's really unacceptable, because that should be the most like ergonomic operation you do. The Rust solution for this, and really every other modern language, is to produce first-class sum types called choice. I'm calling them choice types. Rust calls them enums. I think C# has them as enums too. And then you also need pattern matching. And what pattern matching does is prevent you from accessing the payload corresponding to the invalid or inactive state. So we can have a std optional or std expected that are implemented as these choice types, and then we access them with pattern matching, and that seals off all this exposure to undefined behavior. What Rust does really well is thread or data race safety. So in safe code in Rust, you can't have a data race to mutable shared state. And that's enforced mostly at compile time by the type system. It uses something called interior mutability. It's not actually related to the borrow checker. The borrow checker is involved, but only after you've kind of reduced the problem to a single thread. But for the multi-thread case, the concurrent case, data race safety is provided through interior mutability and the safe and the send and sync traits. And I've implemented those as well. And finally, there's a handful of operations that have to be tracked or checked at runtime. So that'd be like out of bounds subscripting. You should panic for that, or divide by 0, you should panic. The alternative to not panicking is letting the compiler optimize the code, assuming that it doesn't have that poisoned value. So if you have a divide by 0, the compiler may execute or reorder code and then run a path that you didn't expect to take before crashing. That's also a source of exploit. So I've put in support for all 5 of these things. So let's get started with the code. Increase the size of this. Okay. So the first thing you have to do is opt into this new memory safe object model and opt into the new keywords. And you do that with this feature directive. So you say pound feature on safety, and this will flip on the safety feature. Now, all of the text in this file will subscribe to this safety feature. And what that means is that for every token in the translation unit, there's a bit mask, and normally those fields are all 0. But when you turn on a feature, it will emit the corresponding flag for all the tokens emitted from that file. And this lets me change the language in like really drastic ways without sacrificing compatibility. So even though I've put feature on safety before c.io and before this include, it only affects the tokens in the same file. So I can include IOStream or I include like Boost or any other project, and it won't be affected by the changes that are only local to this file. All right, so we've got a new object model that supports relocation and supports borrow checking and supports pattern matching and everything else. And we also have the safe keyword. So int main safe, well, safe is part of the functions type, and now main is a safe function. It has all the same safety guarantees that a Rust function does. So in Rust, things are unsafe, or things are safe by default. In C++, right now, syntactically, I'm making you opt in. But once you're opted in, you can't call unsafe operations, unsafe functions, or do unsafe operations. And you see on line 13, there's a subscript, and I've got an out of bounds one. So let's try to compile safe one. It builds. Oops. And you see a panic. So this is my my custom panic message. It just tells you, the line and column at which the error happened, and it aborts. C++ people don't want to really they don't want to think they're forced into paying a tax. So you need an easy way to opt out of these runtime checks, because there is a cost. Don't believe it when people say there's not a cost. There is. It may only be a percent or two, but it's possibly non-negligible depending on what your domain is. So I've got a keyword, it's unchecked, and that will opt you out of this. So now when I run this, I get familial undefined behavior, right? But it doesn't affect the rest of the safety guarantees. So this function is still safe with respect to lifetime safety and type safety and thread safety. It's just that it's a check just to drop the well, it's a way to drop the runtime checks. Let's do this. All right. It's of course it's unsafe to dereference a raw pointer in Rust and in C++ and every other language that has an interop with C++. So this won't build. Okay, it won't build. It says cannot dereference instar in a safe function. So the alternative is to use borrows. So the borrow syntax is a hat. Int hat is a mutable borrow. It's the same as the Rust ampersand mute or ampersand mute int or I32. Now, will this compile? It's not going to have the same error, at least. Oops. Oops, gotta save that. Okay, I'm getting the code checks out with respect to safety, or with respect to safe keyword, but it fails the borrow checker, which runs at a different stage. So it says use of star p depends on an expired loan right here. Drop of x between its mutable borrow and its use. So its mutable borrow, well, its declaration is right here, and its mutable borrow is at line 10. So there's a drop of x between its mutable borrow at line 10 and its use at line 13. And the drop, of course, is this closing brace. So when x goes out of scope, it's dropped. It's just a trivial destructor, but it still counts. And now the borrow checker knows that this is an illegal operation. So it prevented us from a use after free bug. If I want to make it work, well, I can give int x, keep this in scope, and it'll compile again, right? I'm pretty old school still, so I still use printf just because it's simple. And of course, this is an unsafe operation, so I have to use the unsafe keyword here. All right. Now the safe specifier is part of the functions type. It's just like no except specifier. So F1 through 4, these are all distinct types. And two types that have different safe specifiers are not the same type. So this static assert, I'm comparing, is F1 the same type as F2? It's not, because F2 is safe. However, you can strip off the safe specifier in function pointers. This is like a form of decay. And you can do the same thing with no except. So no except, if you have a pointer to a no except function, that has a standard conversion to a pointer to a potentially throwing function. Same here. If you have a pointer to a safe function, you can convert that to a pointer to an unsafe function. And you can strip off both no except and safe, but you can't add safe because that's unsafe, right? Now, the safe specifier, when I'm in the safe main function, I can't call an unsafe function like F1. So if I try to call F1 right here, cannot call unsafe function F1 in a safe context. If I comment it out, well, I can still call F2 because F2 is safe. it wouldn't be C++ if we like didn't have a ton of features. And there's not just a safe specifier. The safe specifier is programmable, so I can put in like an expression here. And there's also a safe expression, just like the requires expression. So I can put in a unevaluated context, is f of the relocation of these arguments, I have a template parameter pack here, so I have to expand this out. Is this a safe expression? If it is, I'm going to allow this call to spawn to build. If it's not, it's a C++20 requires clause failure and it won't build. So I've got two overloads in this callable. It's like a lambda or something. And I'm going to call the integer overload first. And the integer version is safe. So I expect this safe expression to evaluate true. The requires is true and it's going to build. Right? That build. And then if I put a double here, it's going to call the unsafe overload and that'll be rejected. So it says spawn fails the requires clause, and it tells me what the expression is. And I need this to implement like standard library support. Okay, so this is I'm going to start looking at the borrow checker here. Consider making a string s, initialize it, that's fine. And we're going to try to force a use after free. So I'm going to get a reference to it. This is a borrow. It's a shared borrow in Rust terminology. And then I'm going to drop it. When I drop it, I call its destructor if it's actually initialized, and then I mark internally as being moved. So this is part of the relocation semantics. It's not the same as move semantics. And then I'm going to print. And this is a use after free bug. And the borrow checker is going to flag it. And it's going to give us a 3-point error code where it's going to indicate where the borrow occurs, point B, right here. This is forming an implicit, this is a standard conversion that converts from the L value string here to this reference, this borrow to it. The invalidating action, so when I drop S, that invalidates the reference because now the reference is dangling. And then finally, the use that extends the borrow. And this is part of the live analysis. And Rust has this same 3-point error code, and it's talked about in the LLRFC. It's very good for understanding sometimes these kind of secondary and tertiary effects. All right, so use of star ref depends on an expired loan. Drop of S right here invalidates, or drop of S between its shared bar right here and its use. So the invalidating operation is this drop. I could also relocate it, and relocation is kind of morally equivalent to a drop because the thing has mutated or it's gone entirely. So if I compile here, it says, it's a move of S. So before it said drop, now it says move. The error kind of clues me in on what the operation is. If I don't do either of those, I don't have a use after free bug. So it builds. And if I get rid of this, then I'm allowed, of course, to relocate it or drop it, because now there's no use that extends the loan. And this is part of the live analysis. All right, so I have a string view is kind of a problematic class. It was put in C++ and I guess C++ 17, and there's a lot of constructors and assignments that can make it point to dangling data. That's not possible here. This is a rewritten version that uses lifetime parameters, but has the same ergonomics and the same function names as the C++ version. So let's get a string view and initialize it into constant data. It's just on the heap in the global segment, and then get one on the heap right here. So this is string data that lives on the stack, but it's allocated on the heap. So I've got string view right here, and I can print that. I have S1, and I can print that. Now, the issue is, what if I assign this string to the string view, and then I print it right here? This is another dangling pointer issue, even though I'm not directly dealing with pointers, right? If I comment this out, this code will compile and it'll print something that's good, right? So it's a view into a literal, a heap string on the outside, and a heap string on the inside. But if I try to use SV, now SV is pointing at S2, and S2 is out of scope. So when I build it, I get a borrow checker violation. Even though there's no like borrows in this code textually, the string view is a class that's written with a lifetime parameter to indicate the initialization of the scope of the data it's pointing at. Here's a somewhat more complicated version of this, kind of the same thing. I'm going to have a vector of string views. I'm going to start pushing things into it, and then the vector is going to have a view of all of the scopes of the string views that were pushed into it. So it's a stud2 string that actually holds the data, and then it's kind of moved into, or well, a string view object is created that points into that string object, and then that string view is pushed into the views. And I don't want to allow use after free. So this right here is a pushback into the views vector of the string view into this S2. And since I'm using it down here, this is a use after free. Okay, so use of views on line 37 depends on an expired loan. The drop of S2 right here, and the drop happens at the end of its scope right here at line 27. Drop of S2 between its shared borrow and its use. So the loan is created on this pushback. It's telling me if I were to get rid of the operation that creates the loan, it'll compile, because I don't have any use after free errors. Let's see. I've got the same thing now that works with std initializer list. It's not the regular std initializer list, it's std2. This is really essential because the std initializer list gives you constant pointers to data, and I can't relocate through pointers. And I can't, yeah, for a couple of reasons. First of all, it's constant. Also, I don't own that data. So this, the new std2 initializer list is more like a Rust into iter. It owns the data, and then the vector can iterate through that, transferring ownership from the initializer list into the std vector. And it's the same operation here, right? Because there's a use of views that's spent on expired loan. S2, you see the arrow, the loan is created S2. This is the bad one right here, because S2 is in this inner scope. When on line 24, it falls out of scope, it's destroyed, and I'm trying to use it right here. So if I were to get rid of this right here, compile again. The point is that this is a safe function. There's no way to do language undefined behavior from a safe function without using the unsafe keyword to call an unsafe function or to dereference a raw pointer. Now, you might be thinking well, Rust has a whole bunch of lifetime arguments that you have to put on things like str. Well, that's the same here. You can abstract most of that away, and also lifetime elision chooses sensible defaults for what lifetime arguments should be. But here I'm going to create a function f, return by value of vector string views. And it doesn't take any function parameters. So what other lifetime can I pin it to? Not any really. So I can give this static lifetime. So this string view, well, all the string views pushed into the data have to be static duration. They have to come from constants. So I'm passing a constant right here. Then I'm passing this local. This clearly is not outliving static. So I expect a borrow checker error here. And I want the borrow checker error because otherwise I'm going to use it right here. And that's undefined behavior. All right, found free region static in loan, but S does not live long enough. The phrasing is kind of weird, but that's this nature where I'm trying to return a loan to an object that doesn't have the static free region in it. If I were to get rid of this, it would again compile. Okay. So consider a function that returns a vector by value again, but it's going to take various string views into it. And I want it to return a vector of them, but I can't lose any lifetime information. So that would lead to undefined behavior. So I have to create a lifetime parameter list here. And in Rust, you would write something like, fn func, and then you'd say tick a. I can't use this tick syntax because in C++, we have multi-character literals like A, B, C, D. That's a single character integer literal. So that makes lexing of Rust-style lifetime arguments a non-starter. So instead I use that for an argument, and then the parameter list is like A, B, or C, right? And I need to have the lifetime parameter available in the return type. And that means that I have to use a trailing return type. So it's auto with a trailing return type, see right here, right? And I'm going to return a vector of string views, and the string views are going to have this lifetime. So it's going to have the lifetime of all of its function parameters. Again, right here, I have a string B. And B is not going to live long enough to be printed out right here. So I expect another borrow checker there, right? Use of vec depends on expire load, drop of B between its shared borrow and its use. And it's pointing me out like where the problem is. This call to make vec right here is it's generating a constraint that's associating this data right here with this vector. And when this vector is used later on, it says, oh, well, like not all my, some of my constraints are violated. If I were to pass the A string twice, I'd be okay. And this will print. When you build a borrow checker, there's a lot of like focus on a term called variance. And I think this term occurs once in C++, and it's the covariant return type. If you have a base class that has a virtual function, that virtual function can return a type B. And then when you make a derived type, the corresponding virtual function is allowed to return type D that derives from that base. That's called a covariant return type. That's really like the only place I think that covariance or invariance or contravariance occurs in like the C++ language, but it's a big player in Java when they added generics. And the Rust people realized, well, we could use this work on this like variance solver, not for doing generics, but for doing borrow checking. And it helps you associate directional constraints between these strongly connected component nodes that represent lifetimes on a function and the lifetimes of both the function's arguments and its return object. This is a bit of text from the Rustnomicon, which is the really technical book that describes how Rust safe and unsafe works. If you didn't have this variance analysis, this program would execute and it would be unsound because you end up having a use after free trying to print this string hello right here after it's written with this local variable string right here, world. So worlds get pushed into a reference right here, and you get a dangling pointer, but you can't just use ordinary borrow checking for this. And some of like the efforts that the lifetime annotations for the I think Chromium and Clang have been working on that, like that's an insufficient thing for encapsulating the kinds of constraints required. So I took this variance example and I transliterated it in C++, same thing. And if I build mine, I get a very similar error. So what you have is after the front end runs and you build abstract syntax tree, you have to lower to LLVM. But before doing that now, I have to lower to mid-level IR, which is a control flow graph that's a little simpler than LLVM, but it has a bunch of metadata for doing initialization analysis and drop elaboration and borrow checking. And part of that is a battery of solvers I run. The first solver is the for initialization analysis. It's a forward data flow, and you just run it until it converges, and you find out which objects are initialized or potentially initialized or definitely uninitialized. And the other one is live analysis to find which references or which borrows or which borrow-like types, including string views, because they have a lifetime parameter, finding which one of those are live. That requires a reverse data flow analysis where you start from the terminators of the graph and you work your way up to the root. The variance solver is like a third flavor of solver that basically makes sure that you're not allowing any unsound behavior when storing through mutable references. All right. A lot of people say that modern C++ is safer than like C++ 98 or C, and that's really not always the case. So this is very basic old school C++ that uses, indices to loop through something. And I just want to loop through the contents of the vector and then push the odd elements to the back. Works fine. It's well defined. I'm not doing any like out of bounds operations. But let's use a ranged for. And now it's going to get the begin and end iterators into this vector. And now whenever I do pushback, that may create dangling pointers in the iterators, but that's not something that C++ static analysis will track. So if I compile and run this, undefined behavior. Okay, this is the same thing, but with the safety keyword on it. I'm using std2 vector. Now, it's like this exact same code, but I get a borrow checker error. Mutable borrow vec between its shared borrow and its use. So this prevents me from using an iterator or any other type that was invalidated by some intervening action. If I comment these out, well, this is just normal, a normal loop, and that'll build. So you may have heard that like Rust is incompatible with C++ style iterators. That is true. This does not use C++ style iterators. I have an interface. An interface is a customization point. It's like a Rust trait. So when you write a range for loop, it checks if your type right here implements this interface. If it does, it uses these functions, and it uses a slice iterator, which is modeled like a Rust iterator. So the slice iterator, or maybe it's close to like a C++ range. It includes a begin and end pointer, and then a next function. And so when you call next, it will move using relocation the next bit of data to the optional and return that. And if there's no available data because we're already at the end, it'll return .none. So this is type safe, right? And it supports relocation. And of course, it can be checked by the borrow checker because it has a lifetime parameter A. So these are raw pointers, but this phantom data right here gives them the variance of the borrow. So it's as if you're using the borrow here. Okay. I've got first class tuples and a new first class array type. I need first class tuples because you can't relocate through C++ to tuple because that uses getter functions, and a getter function requires moving through a reference. You can't do that. You can only relocate through objects that you own, because the compiler has to have bit fields indicating which places are initialized or not. When you move from something, you have to be able to clear out that initialized field. So when I opt into the safety feature, it enables these types. So you can define a 0 tuple, a 1 tuple, 2 tuple, etc. You can nest them at your leisure. You can create expressions. The critical part is that naming subobjects of a tuple gives me a name in the IR. Oops. What did I do? Wrong program, sorry. Oh, here we go. So I'm saying T3.0.0.1. Well, this lowers not to a bunch of function calls like a cascade of std-gets. It lowers to a place name. And the compiler, the mid-level IR process, it loops over all the places and says, oh, well, here's a name that is being used or moved, so I have to be able to allocate initialization data for it. And this supports relocation. I put in some more diagnostics to help you understand when you can relocate through things. So if I build this test, I get 3 safety-related errors. I can use the tuple, but I can't relocate. And rel is the relocation term. This takes an L value and it returns an R value of the same type, and it leaves the old source uninitialized, and then you can't access it. This is probably marked safe. Oh no, that's fine. I'm using std tuple. That's unsafe. So I'm not allowed to relocate through std-get because that would require relocating through a reference. I'm allowed to do that. I can't relocate through something that uses dynamic subscripting. So this is not const on purpose. I want to make it clear that this is a variable subscript and I can't relocate through a variable subscript. And I can't relocate through the subobject of a global variable like G because this function doesn't own that global. It only owns other locals. And this is a rather wordy, but I hope like informative set of error messages indicating that, an own place is a local variable or subject of a local, and you can't relocate because it involves a dereference of the L value reference right here. Oh, that's pretty ugly. I've changed the syntax highlighting on this. Okay. Choice is my new first class sum type. That's a discriminated union. You can initialize it with this like dotted syntax. So if you have a choice primitive and there's a field I8, I just can say .I8 or .I32 or whatever, give it the initializer for the payload, and then it creates a new primitive, or new one of these. And then to access the values out, you have to use pattern matching or like the extract operator question mark, same as Rust. This prevents you from accessing the wrong field. Again, C++ did expected. It's new to C++ 23. When you look at the docs, and like if you use star on it, that's undefined behavior if the error part is engaged, and that's really bad. And this prevents that from happening. So you can use, indicate which field you want, and then there's additional tests you can put in. This is the same syntax as Rust. I took the range pattern from Rust. There's 6 of these. So this is between 100 and 200 inclusive. And this is between like 1,000 and 2,000. It's half open interval. It's also does exhaustiveness checking. So if I were to comment out this, obviously there's a lot of cases here that aren't supported, and I would expect some error to tell me that. Right? It says, well, match expression is not exhaustive. It tells me the field types that I'm not checking right here. I also have this is kind of an improvement on Rust. I have some cool new features, like the curly braces here is for variant style matching. So I've got 3 different fields that I have the same kind of payload, UN64. So I can match any of those fields just by indicating that the payload kind. So if it's any of these UN64 fields and it's 500 or 1,000 to 2,000, return 4, et cetera. It's normal pattern matching like most other languages have. I also have a concise form right here, which is the match expression, concise match expression. And it just tells you, like, do a query and tell me if it's true or not. So in this case, dereference the self, and self is like primitive. So you can add member functions to these as well. So these are kind of like classes, but I mean, you can add member functions to them. So you can let it query itself. So if it's an I8, I16, I32, or I64, it'll return true. And this is the equivalent to Rust's matches macro. Rust uses a lot of macros. It has a better macro language, and I didn't really want to build a new macro language, so I thought it'd be better just to add more first-class features, because you definitely don't want to use C macros for this kind of thing. The other thing you can do is open new control flow inside of a match. This is really critical, or else your pattern matching is just a toy. Fortunately for me, I actually already implemented these things called expression statements. They're in GCC. They're somewhat obscure feature. It's only used a few times in like the standard library, the libc++ or libstandard C++ implementation. But it lets you open up a new compound statement inside an expression by using the parentheses and the brace syntax. So now if this it's an optional vector of int, if this is engaged, then it's going to match the dot sum. I can bind to the inner part right here, and then I can like loop through and add up all the values and then yield the value of the last expression. So it's called the tail expression. Otherwise, I'm just going to return 0. It's great because it makes sure that I'm not accessing a disengaged optional. If you want to check the definition of optional here it is. There's default none, which default means this was initialized if you want the default constructor, and there's a sum_t, and then there's some member functions here. Rust has something like 50 member functions on option and result, which are equivalence of optional and expected. So you could probably add more depending on what operations you want to do if it doesn't have the field that you expect it to have. But yeah, so you can say like, okay, or I'm going to match on self. If it's some, then relocate the value out. If it's none, relocate the error. And this is consuming. So I'm not binding to an L value reference to self or a borrow to self. I'm binding on self itself. So like this will relocate the object into this function, relocates the payload out, and then everything gets cleaned up. It's called a consuming function. It's really necessary for having relocation semantics that work. And again, it's new to this object model. All right, this is really the last trio of demos, and then we'll take questions. This is my favorite part of the Rust safety model, which is its robustness with respect to data races and concurrent programming. And it does this mostly at compile time using very inventive type system. The challenge for me was to make a system where if you are in a safe function, you can't create a data race to shared mutable state. So the first thing I'm going to do is create I'm going to try to fool the system here. I'm going to try to mutate this string s without using a mutex around it. And the type system is going to prevent us from doing that. So I'm going to compile this, and we can take a look at the error message. All right. So what I'm getting right off the bat is that the constraint on the thread constructor fails because this std2 send concept or its interface is not satisfied over basic string borrow. So a borrow to a basic string is not send. So when I look at std2 right here, and I look at the thread class, this is my safe thread class that wraps the ordinary C++ thread class. So you see as a data member, regular stud1 thread class, and this is my thread class that wraps it and gives you a safe interface around it. And it has a lot of stuff right here. It's like really important that it be safe. And what was violated right there is this concept right here. You see that the callable has to be send, and the arguments, all of them have to be send. Well, what is send? Okay, send is an interface that is a marker interface. In Rust, it's called a marker trait. And it's an auto trait. So the compiler automatically goes through and using the rules of inherited mutability says, this object is safe to copy to other threads, or it's safe to share a shared borrow to other threads. It's only safe to do that if it has like value semantics. So you can't send a mutable reference around because that would violate the law of exclusivity of having one shared or having one mutable reference or multiple shared references live. But you can share like shared borrows to objects, assuming that object itself is sent. And it's a weird system, but it's created a really durable environment to build like higher level abstractions like senders on top of. So it's impossible to actually fool the system. So right here, I'm not allowed to send this mutable borrow of string s to the entry point because this mutable borrow is not, it's not send, but a const borrow is. So let me try to do that. And I can't append to it anymore, but I can print from it. So now I'm going to try to take a shared borrow to s and send that to the entry point and print. And you think, well, that should be okay, but like S right here is on the stack, and it can very well go out. Definitely will go out of scope prior to being printed from this other thread. So this would be a use after free bug in this entry point thread, and one of the 15 of them. So it's the worst kind of thing. It's like non-deterministic. It has to do with threads. It's going to be like a real pain to debug this in a practical situation. So how does the compiler prevent this from running? So let me build it right here. It says S constrained to live as long as static, but S does not live that long. And it points to this right here. It says this S should live as long as static, but it does not. I'm like, well, why is it telling me that? Because if I look at the thread constructor, it has another Rust feature, which are lifetime constraints. So where you normally introduce lifetime parameters, you can also put like where, which would be an outlives constraint. So I'm saying that all the lifetime parameters associated with F and all of them associated with args have to outlive static. So this prevents you from passing it anything that has like local or automatic storage duration. It has to be static storage duration to get through, and it has to be send. If it doesn't do that, that's not an error in the front end, but it's an error during borrow checkings. This is later on during the mid-level AR. So in this example, trying to pass just a mutable borrow to a string or a shared borrow to a string, we were prevented from doing that by two different mechanisms: send and sync in the first case, and the second case by the requirement that the lifetimes on the argument outlive static. Okay. So we can alleviate the issues from the previous example by using a shared pointer. Shared pointer gives you atomic shared ownership of an object. It doesn't give you like shared access to it. It doesn't include any synchronization. So even though it's well defined to copy shared pointers between threads, that's not sufficient because you're not allowed to mutate the data or to even read the data outside of a mutex, right? So it's an improvement because I'm not going to get a use after free bug from the data going out of scope, but I could still get data races that will create undefined behavior, like through a partial, the write is partially done when some other thread starts reading it out. That's like super difficult to debug because it's non-deterministic, and you might only find it when you've deployed your software. So I want this to fail, right? Because I'm copying the shared pointer into the thread entry point, and then I'm trying to append to it, and at the end I'm joining. So why won't this build? Okay, this is a type system error. It says cannot bind the explicit object parameter. This is a mutable borrow to a string to this expression, a PR value, a const borrow to the string. So you kind of have to understand how the Rust solution to threading works, and that solution is interior mutability. You're only allowed to have one mutable reference, or like you can have as many shared references as you want. So like, doesn't shared pointer violate that, right? Because shared pointer gives you shared ownership, but doesn't that imply shared mutation? Well, it doesn't, because if you start or arrow with the Rust shared pointer, which is called ARC for atomic reference count, that's returning a const borrow back, a shared borrow. So it doesn't matter if you call it with like a mutable L value, it's returning only a const view. So you can't actually mutate anything through a shared pointer. You can use it, but you can't change it, right? And that's really surprising, right? So I can print this out. The problem was the append. The append requires mutation on data, but I'm not allowed to mutate that data. So that builds actually, if I link it with pthread, it'll work even. All right, so now I have 15 threads that are spawned up. They say hello thread, and there's no data races. There's no use after free. Everything works because there's shared ownership that prevents the use after free, and then the prohibition on mutation in the shared pointer prevents this append from creating a data race. So the question is, like, how do you mutate shared mutable state? Well, you have to use a type like a mutex, and the Rust mutex and now my std2 mutex uses interior mutability to do a const cast in a safe way. You have a bunch of users that have constant references or shared references to this common object, but you have to create at runtime now a mechanism to only take one mutator at a time. So you're creating your own lock to a resource, right? It's a single write, multiple read lock that for single-threaded code, it can just be a regular like non-atomic thing. But for multi-threaded code, you need like an operating system synchronization primitive, like a mutex in there to prevent violating that law of exclusivity. If I look at the mutex class here, this is my mutex class. I have to mark it as send and sync based on what the attributes of its argument are, right? And now I have a function called lock, and this is just going to take the mutex and sit on it until I get it. But I'm giving it a const reference to self, and it's giving me back a lock guard that's mutable. Like this is a new value. And what's going on here internally under the covers in a class called unsafe cell. And if you know Rust, like unsafe cell is kind of the acorn from which all this like mighty oak of interior mutability sprouts. Like this unsafe cell right here is a systematic way that's safe to the compiler, like safe with respect to type aliasing, to go from a const reference to a mutable reference. So when I gain the lock, this is me getting the lock to the actual C++ mutex object right here, right? So when this returns, it means I've got exclusive access to this mutex, and now I can return this lock guard. And by doing so, I'm stripping away const. And then the lock guard itself will give me a mutable borrow to the interior data, right? So it's the lock operation that does this const cast that strips off const, and then I can say, well, lock guard, give me access to the data. So I'm gonna create a mutex of string. Like the string is part of the payload. The mutex is now a thing that wraps the data. And you could have a shared mutex that is more sophisticated. You have to indicate I want like a read-write lock or just a read lock, and it would allow multiple readers that way. So I'm passing a new string called hello world. I'm initializing a shared pointer to a mutex. The shared pointer is safe shared ownership, and the mutex is safe shared access or safe shared mutation. And I'm copying the shared data to the entry point. And now I want to get the lock guard. So this gets me down to exclusive access. And I'm going to call borrow, and borrow is going to give me back a mutable reference. I'm going to append, and I'm going to print back out. Run it. You see, I'm calling. I've included uni stdh, which is another archaic header in Unix, and I'm calling sleep. It's got full second granularity. So one is like a good second of waiting, and you see all these functions, these entry points, they all sit on the lock right here, and they're given the mutex one at a time. They borrow a mutable access to it. We have not violated the law of exclusivity here because the mutex itself guarantees at runtime that there's only one live mutable reference to the interior data. I append this fire emoji, I print it out, and then I sleep. When they're all done, it gets cleaned up as normal. So let's try to game the system. Let's try to access data and cause a data race. And you see that between the borrow checker and all the constraints on the thread constructor prevent us from generating a data race. The first thing is let's drop the lock guard. And when I drop the lock guard, that runs the lock guard's destructor, and the destructor will call unlock on the original std mutex. And that will let another thread waiting on deck come and start mutating that string. And that's going to create a data race because I still have to print the string. So if I drop the lock guard and then print the string, that may print the string while another thread is mutating it. And that is a potential security vulnerability, right? So let's try to compile that. What do I get? I get a borrow checker error. It says use of star s right here depends on an expired node. Drop of lock guard between its mutable borrow and its use. So where is the mutable borrow? Right here, line 16. It says right here, and the invalidating operation is a drop. So it tells me what the problem is, that I'm this star s depends on the lock guard being in scope. By dropping it, by leaving the mutex, I've opened myself up to this borrow checker violation. Okay. Instead of dropping the lock guard, let's just try to drop the data. So I can, when you run the destructor on a shared pointer, it's going to, decrement the reference count. If reference count is 0, it's going to delete the object, and that's bad because I could have a use after free on the string itself, and I don't want that. So what happens if I drop the data? I get a different borrow checker violation, right? It says drop of data between its shared use. Between its shared borrow and its use. The borrow is kept live by the drop of the lock guard declared at line 11. So at line 11, I have a lock guard, and this lock guard has a non-trivial destructor, right? A user-defined destructor that's run when it goes out of scope right here. And that destructor will call unlock on the interior on that mutex. When I drop data, that disrupts the lock guard's ability to call unlock internally, right? You've created this network of constraints. And if you violate any of the constraints, you get a compile time error. So what is this really doing? I have to print the mid-level IR. And this is the IR just for the entry point, because the error is in the entry point. So it's just going to stop compiling when it finds a bar checker violation. I have a list of local variables. And I have a list of regions. So regions are what you call lifetimes when you're writing a compiler. And every function call is going to generate these strongly connected components of function lifetimes. And these get their own regions, and then the loans get their region right here. So that's a loan, that gets a region, right? And then you generate all these constraints. So whenever you do an assignment or you make a function call and there's lifetimes involved, it's going to generate constraints going in different directions. Usually there's a constraint going from the argument through this SCC for the function and then out through the result object if there is one. This creates like a network of constraints. And then you run the constraint solver and you grow these regions, which is a form of live analysis to find all the loans in scope. This is the list of loans in scope. These intervals are points in the program. And the final borrow checker operation that actually is responsible for raising most of these errors just steps through every instruction. It says, at this point in the program, let's say the point is 16. It's going to say, well, that's in scope at 16, that's in scope at 16, that is, but these are not in scope, so these are irrelevant. So it's going to look at these three loans and it's going to say, is there an invalidating action? Is there a read on a place which has a mutable borrow because that is illegal? Or is there a write or a drop or a move or something else on a place that has a shared borrow and that's illegal? So it's kind of created a system where it's impossible to violate this law of exclusivity and generate use after free bugs or like iterator validation bugs. And that's all done at compile time. So I'd be happy to like talk about, I mean, this is just a real quick overview, but I think this is really satisfying to me because as you can tell, if you look at this kind of new standard library, I use a lot of existing components in here. I'm not saying get rid of your existing components. And if you have code that's well tested, which obviously is like, you know, every implementation of the standard library is well tested, Boost is well tested, a lot of like EASTL is well tested. You don't have to get rid of those, but you have to be able to use them in a safe way. And you can build safe wrappers around existing code that will test the invariants mostly at compile time and prevent you from hurting yourself. So I think there's like a good kind of evolution path for iteratively, incrementally hardening existing code in a way that it looks and feels like C++. I mean, if you have you know, something like this looks like modern C++, even though the object model is completely different. It uses, you know, relocation and the borrow checker and drop elaboration run, which is really a Rust thing. So I think it's a pretty cool, you know, marriage of features. And yeah, so I'm happy to talk about it right now. If anyone has a comment.
Eddie Nolan has a hand.
Oh, let's see here. Just, is it possible to unmute yourself or do I just click on your hand? What do I do? I don't know how to use
Uh,
mute.
I can just unmute myself.
Oh yeah, just do that. This is harder than like writing borrow checkers for me. So
So the first, I just have a kind of a minor question, which is, are you aware that the current reflection proposal that's moving through the committee also uses that unary caret for reflection, so that kind of conflicts?
yeah, they should choose a different token because you're going to use the borrow one like, you know, like all the time. So yeah, I know there's a conflict. There's only so many tokens in the world.
I think this one is actually conflicted with Objective C, so it will change like in the reflection proposal.
Yeah. The Clang people are upset about the current reflection proposal because of the conflict with Objective C++ as well. So it's not even certain that that's going to be what the reflection standardizes on.
Yeah, I don't want to like, I'm not really like sold on any particular token spelling. Like I mean, it's like there's a lot of material here and we're talking about like really deep changes to conceptual object model. And I don't really care about fighting about I'm not saying you want to fight either, but yeah, like all this can be ironed out, I feel, especially since I have the
Yeah.
ability to change things. Like I can change like any feature on a per file basis. So if you need some, like if I have on safety, I mean, this could change the token for doing reflection, right? Like, you know, I could have I don't know, do reflection keyword or token or something. Like I could make that a reserved word, which does what the hat does in the reflection proposal. Like there's ways to work around anything when you can do compiler extension. So there, I don't really believe there's a true conflict, because you know those conflicts can be mitigated just by changing one or the other in the scope. All right. Okay.
Sasha K is next.
Do I just,
If you don't mind, I can tell people who's.
Yeah, do
I'll
that.
keep
Yeah.
a
Thank you,
head.
Ben, for
So,
doing
yeah.
that.
Sasha
Yeah.
K.
Yes, hello. So, could you go back to your example with just the thread without the shared pointer and the mutex? I got
This one?
yes. So I got a little lost when you were talking about like the lifetime constraints, like how the thread can only take static lifetimes or something. So couldn't you just constrain the arguments to have the same lifetime as the thread, and instead of having it be static lifetime? Or did I misunderstand something?
The problem is that the thread is like asynchronous, and it's not if you make it, that would work for normal functions. So when you call a normal function, you know it's going to return before the calling function goes out of scope, right? The function calls are just nested, but you don't know that with a thread. You don't know when the thread's going to return.
I see. Oh, because it's not
So,
like the J thread or whatever that destructs itself on.
well, it does, but that's a high level like concept that's not available to the borrow checker. If you were to like, I think that's a level of like knowledge that would not be worth implementing in a borrow checker, because the system's already quite complicated. And like the Rust, if you look up Rust thread spawn, it has the exact same static constraint. I think it would be too easy to find soundness holes if you were to allow it to take information terms that have you know, non-static lifetimes. You know, if like what happens if you throw here or find some way to leave before the join? You say, well, maybe the destructor, does the destructor do a join? Then it becomes like, well, the destructor does a join, and
Okay.
no, I don't think that would work even. No, yeah, that wouldn't work here. It has to be static, because if I were to exit here, well, let's try throw or something, right? That cleans up S, but these threads are still running, I think. Like,
Right.
you know what I mean?
Well, but as soon as you leave the scope, the threads would get destroyed, right?
No, I don't think in a way that's sound, because I think like eventually they'll get destroyed. Right? But are they going to get destroyed prior to reading? I mean, the synchronization takes time, right? It's not immediate. So when I guess the question is like, does the destructor wait around? I don't know. The answer is this is the way I think it has to be implemented in the end.
Okay.
It's just really hard to think about all the scenarios. Put it in a shared pointer. Just let shared ownership. I mean, in reality, you're going to have some big struct of shared state, right?
Yeah.
And
Yeah.
that's just the Rust way. I you know.
Okay.
Yeah.
Okay. Sounds good. Thank you.
Yeah. Yeah. So Christian says this is a known pattern in Rust. Yeah. I don't want to like mess with that formula, because I think this is the part of Rust that is like least objectionable. It's because leaks are safe, so the thread can. Oh yeah, good point. For good but sophisticated reasons in Rust, you can leak an object, and by that I mean you don't have to call its destructor. I actually have that in here. It's called is it called manually drop? Yeah, there's a class called manually drop, which is a way to intentionally leak things. And if you were to leak the thread object, then its destructor would not be called.
Got it.
And that's safe. And that's safe. And if the destructor's not called, then it's not going to join, and you're going to have use after free. And you say, well, it's safe because it doesn't create undefined behavior, right? It just may create something that leaks, and leaks aren't really UB in the CVE sense. And it's a safe operation. So this is like a known thing. Yeah, I don't think it matters if right. So I think Christian's explanation is better than mine. I should have had that at my disposal. The point about the safety model is that even if you're malicious, even if you want to create undefined behavior, you can't do it in a safe context. That's why answers like, well, just don't do that, or who would do that? Like there's going to be somebody who does that. I mean, we know, was it Hiram's law or whatever, like every weird aspect of C++ has been exploited by people, and that's going to be the same here. So you really do need like a provably safe thing.
Right. Being careful doesn't scale.
Yeah, that's right. Right.
Okay. Thank you.
Got 3 people in the hand queue. Yol Na, you are next.
Oh, yes. Thanks, Sean. I just have several clarifying questions. So the safe keyword is not part of the overload resolution, right?
Okay, good question. It's the same as no except. So if you have a function that takes a type, and you can discriminate on no except or safe in that type. That's part of overload resolution, but it's not part of overload resolution in the sense where if you're in a safe function, it'll only find and consider candidates that are safe functions, right? It's the same as no except there.
Right.
Yeah, but it will prevent you from calling an unsafe function from a safe context.
Got it.
Yeah.
Got it.
I would say one good bit of philosophy is that if you were to take a sound Rust program that compiles and mark every function as unsafe, it's going to still do the same thing. It's going to still be sound, and its meaning's not going to change. Safe keyword is just there to slap your hand when you do something dangerous. It's not actually a safety mechanism in itself. And I did that here. That's why with these like the checks for array subscripts, or I didn't indicate this one, but it's the same thing, like the check for divide by 0. It doesn't matter if you're safe or not. It's always going to do the check, and you have to opt out from some other mechanism, because I don't want safe to be something that you expect. Well, I have different behavior depending if I'm on a safe or unsafe context. It's always the same behavior if it builds.
Got it. Makes sense. So I have a quick question as well. So I assume you also prevent array subscript on a row pointer, right?
Well, raw pointer itself is any dereference or a subscript that's invalid. Yeah.
Right. So for that, you would expect the user have to rewrite it to be like to span or.
Oh, okay, good. Well, yeah, I should have had a thing in here. I don't have a sample, but I have a type which is a slice. So in Rust, you have an array, and you also have a slice, and a slice is an incomplete type that. Here, let's do this right here. Let's do it. Func. It'll be like const, ints, dyn. Dyn is for type erasure for interfaces, but I also use it here to indicate a slice. So this is a slice type. It's like an array, but you don't know what the length is at compile time, but you do know what the length is at runtime. You do, because this reference right here is 16 bytes. So it's got it has a data pointer, it's 8 bytes, and a length which is 8 bytes. So let's call func, and I can pass it this right here. See that back. Oh, it's perfect. It compiles. So I can even probably print out. Let's do this. Int. Live coding. Slice. Okay, let's see if this is right. So we were saying we'd expect to get a panic if index is out of bounds, but we don't know what the bounds are here at compile time. We know what the bounds are at runtime. Right? So let's pass 17, and we want this to panic. Who knows? Oh, a panic, right? Subscript is out of range of the slice type. So this is the same as a slice. And you could build a span out of this super easily. And the span would just be, let me show you the basic string view is basically a span, right? Over characters. Oops. String view. Where'd it go? Where are you? 36 string. Here we go. So internally, this has a slice internally. So this is just like a span, right? So this is the 16 byte fat pointer. It's an incomplete type, but pointers to it or reference to it or borrows to it are complete, 16 bytes, and you can extract the length and the pointer. Yeah.
I see.
So same as Rust there.
That's cool. So like, yeah, final question. So how was the adoption effort? Do you have experience?
The what?
How was the adoption effort, like time or?
Okay, so I think I've been kind of planning doing this for about 2 years, like since the National Security Agency and like White House. I mean, that I think the real hubbub started about 2 years ago. So I started looking at it. I would say about 18 months ago, I started doing the preliminary work, and this has been really full time, like 60 hours a week, 70 hours a week, or whatever, maybe for the last 14 months. To
Sorry.
implement safety.
Sorry, I meant if you want to apply this model to existing project, how was the like experience like adapting?
I don't know. I mean, this isn't complete yet. So
Mhm.
I have like all the major components, but I don't have complete coverage of the AST. So this requires a new backend for the compiler, right? Normal C++ compiler, you parse the inputs, the tokens, you build AST, and then you lower that to LLVM or you lower that to whatever your backend is. But here you have to lower that whole thing to mid-level IR, do these
Right.
tests, and then you have to like do drop elaboration, which changes the mid-level IR, and that's to account for the relocation, because you can have like fragments of things that are initialized. So that requires changing the mid-level IR, and so then I have to lower the entire mid-level IR to LLVM. So that requires like a new backend be built from scratch. And I don't have all the coverage yet. So there's still AST nodes that I don't support, like for things like involving, virtual inheritance is not in, or exceptions I don't even have in yet. That's just like 2 days of really painful work to get the landing pads generated correctly. So I'll know more about the effort to migrate things once I have like a full compiler, because I have to be able to,
Right.
express any operation and have it go all the way to a binary at the end. So I can't really high level question like, well, what effort is it to harden or to make safe like existing code? I don't know. I think that really depends on what the project is, and that's just software engineering, I guess. I don't have any like super wisdom on that.
Got it. Yeah.
Thanks.
Thank you. Makes sense.
Right. 2 hands in the hand queue. Eddie Nolan is up next.
Hey, so I just wanted to return to like the same thread example that was discussed beforehand. I think that was thread 3.
Thread 3?
Or no, it was the one that was about this one. So the first thing is, I think that like my understanding of the way std thread works, and I posted it in the chat, is if the thread does not detach automatically, you have to manually invoke dot detach on the threads. Otherwise, if they go out of scope before they've been detached or joined, they'll just terminate.
Okay, but does that create a soundness hole here or not?
No, I don't think it creates a soundness hole. So I mean, it's just a point of clarification. It doesn't actually affect like any of the safety properties. But what the other thing I wanted to ask was like, so is there any way of like changing the specification of std2 thread such that like supposing you moved that string s initialization above the vector of threads, and supposing that you had like a for example like a C++20 J thread, which you cannot detach, and which instead of aborting in the destructor just loops forever, so that like you cannot like you in that case you wouldn't be able to have the string. I guess maybe you'd need like a std2 J thread thing, but then maybe you wouldn't need to require static lifetimes on all of the parameters.
I think an example this trivial, it's easy to think, well, I can be smarter or more permissive than the borrow checker. But in a real example where you have shared state that has lifetimes like of many things, like your ability to reason about the code like will disintegrate, and you're going to need hard rules. And I think that the borrow checker rules and the send and sync rules and the constraints on the thread constructor are really built for like never being beaten, right? If someone comes up with a soundness hole related to data races in Rust, they take it super seriously. They consider it like a day zero exploit. It's not an exploit at all. It's just someone in their own compiler intentionally like broke the system, and it gets patched. But with if you try to kind of make it more hand in glove to accommodate these kind of cases, I think you're going to weaken the borrow checker to the point where it will become unsound, and that you will find soundness issues later on. I mean, that's the problem with doing a demo like this, right? You can see points where you say, oh, the borrow checker is like overly strict, but it's like that because it has to be robust against kind of adversarial code, and I don't think we can drop the static constraint. Also, if you want to drop the static constraint, I guess like take it up with the Rust people or something, because I just copied their lead on this. My goal was to make this as safe as Rust. You know.
Okay, yeah, that makes sense. Thank you.
Herb, you were up.
Yeah, my question has been partly touched on. So first of all, great
You were
work
very
with
quiet,
this.
Herb.
Hi, can you hear me better now?
A little bit.
Yes.
Can you keep
Oh,
increasing the
here,
volume?
let me try a different
good.
microphone.
That one works.
Oh, good. That's the one. It turns out that's the one it was using. That's why. Okay. Too much technology. First of all, like great work. This is really, really super interesting and an important thing to be exploring and well presented. One of the things I always come up against is customer has a multi-hundred million line of code base written in today's C++ with unsafe functions, of course, that's using today's stood shared pointer, today's stood mutex, today's stood tuple, etc. Have you given thought to how much benefit can I give in terms of making this adoptable? How close can I get to, I just write the word fast on a bunch of my functions and it works, or the impact is minimal? Or do I have to start adopting wrapped threads or alternative tuples, or like where's the adoption? Is it a step curve? Is it a ramp? How smooth can the ramp be made?
Right. If you go into this with the idea that I need to put safe specifier on all my functions, it's going to be like super painful to deal with large code bases. But I don't think that should be the goal. The goal is to reduce exposure to unsafe operations. And you can do that one tiny step at a time. So look at like all your types, and there's, like thousands of user-defined types in a program. Take your unique pointer right now, which has undefined behavior on star, replace that with std2 unique pointer. And then wherever that thing is used, it only be used a handful of times, right? Because any one declaration is usually only used a handful of times. Those may have to be updated if they do something that is, not supported by the new API. And you make these changes, you reduce your exposure to unsafe code, without ever putting the safe keyword on, because the safe keyword is like a really high bar to clear. That says my function, and transitively every other function it calls doesn't have undefined behavior. That's like too much of a promise to make when starting with a bunch of existing code. But that's not the goal, right? The goal is to reduce exposure to unsafe operations or unsafe APIs, and you can do that, I think, like very fine grained. You say, well, it's just like spitting into the ocean. Perhaps that's true, but like, I mean, companies that have huge source bases have huge source bases because they have a lot of like employees. So I guess if just the case of like getting your employees at some point with some organizational strategy, and you set our priorities. You say, well, like we think our CVEs are on bounds overruns or on lifetime safety associated with ranged fours or whatever, and you go and replace those things. That's not making your code safe, but it's reducing your exposure to unsafe APIs. When you can finally put the safe keyword on, that's great, but I don't think it's like it's safe or nothing. Okay. It's really about just reducing your exposure.
And that makes sense. And the biggest low hanging fruit is out of bounds because it's like two of the top 10 CWEs from last year. And so even just narrowly bound safety improvements would be important. Just one quick follow up, like one difficulty we found, the C++ core guidelines, when we standardize std span, we still have GSL span, which is the same, except it's required to be checked or checkable, which is the only difference from std span. One of the things that we have just found, which has surprised us, is how hard it is to get people to adopt it, because it's been designed as a drop-in replacement for, you know, pointer pairs and things like pointer length parameters. And the pattern, the anti-pattern that we found is not all the time, but some of the time, you can't just use it locally, because then, oh, but to change this pointer length pair to span requires changing call sites to pass a span instead of pointer length, things like that. To what extent might that, I don't know to what extent that might prevent even tactical adoption of, say, std2 unique pointer versus std unique pointer, but it's something to think about anyway. We were surprised, at least I was surprised, how hard it was to get people to adopt just one range type.
Right, I think that's good, but I think there's a data point, which is the Chromium effort to replace all the raw pointers with the Miracle pointer type, which is, you know, it's a shared pointer and has a control block, and I think they cut down their total number of use after free bugs by 50%, which it's kind of sad it's not higher than that because it's a really huge surgery, but there was willpower to replace, you know, one of the most common types you find, which is pointers with a new smart pointer. And, you know, they got it done, and it was a mixture of like automated techniques and manual techniques and whatever else. Yeah, I don't know. I don't have the leverage over people to make them change their ways. Yeah, I don't know how you get people to change, but I think at least here you have the promise of rigorous memory safety. So maybe that's more of a motivator than like saying, oh, it'll be partially safe, we have partial coverage.
Yeah, and certainly, I mean, the answer Rust gives and CPP2 gives, and it is for new code. It's like, so new code is great. I'm always interested in how much can we do for old code, but this is great. Thank you very much. That answers my question.
Okay, thanks.
2 hands in the queue, so let us know whenever, you know,
yeah, why don't you
ready
call
to
out
wrap
that?
things up.
Oh,
So
yeah, call out the who's next in the queue.
so right now we've got Chris in the queue, and then I'm in the queue after that.
Okay, Chris.
Hey, so yeah, thank you very much. That's very impressive. I just have a few follow-ups from the implementation point of view.
Okay.
So you mentioned that you changed to MLIR. I was wondering how much effort that was for you to change it from the IR to MLIR.
Oh, it's not MLIR. So
No,
MLIR
just
is
medium.
MLIR is a like specific project of LLVM, right? This is a generic mid-level IR, but it's not like LLM's mid-level IR. So
I see.
It's a bespoke thing. I mean, you can see it right here. MLIR is really complicated. And it's based on like creating dialects if you want to do something like MATLAB or like a Fortran kind of language, and you have different kind of, you know, loop transformations, and you have reductions, and it's like AI, you know, needs tensor operations. This doesn't do that. This has a different reason for existing. And the reason for existing here is just to get the simplest possible control flow graph representation that still has all this like crazy amounts of metadata. So I think mid-level IR, the MLIR of LLVM doesn't do that. I think the Mojo project may be extending it to do that, but I don't know, but it's not in there right now. Like right now, out of the box, MLIR does not support borrow checking. So.
Well, okay. Well, that was my understanding, but maybe not. So yeah, thanks for that. So following on that, I was wondering about the compilation times. You know, Rust has, you know, a lot of this checking, as you pointed out, and it suffers from that. I was wondering whether you manage to make that fast.
I don't have enough like diagnostic data right now or telemetry data to tell you what the overall runtime of the borrow checker is, compile time of the borrow checker. That I think is going to require me to like finish coverage, get a complete C++ compiler that lowers to mid-level IR, and then I can test like going against the current backend versus the new backend. The borrow checker itself is pretty fast. Most of this is done with like bit vector manipulations, and even without using SSE or anything. I mean, when you do data flow analysis, you're like combining 64 bits at a time with just regular registers. It it converges super fast, the data flow analysis. And the borrow checker operation is also really fast. I think they said it's maybe like 25% of the compile time in Rust. But I think Rust is slower probably because the generics, like Rust generics are checked at definition, templates are checked at instantiation, right? And when you check at definition, you have to build like archetypes, which are quasi types that have the interface, which is a union of all of the traits that were expressed on that function declaration. And that's a really expensive operation. I tried doing that. I tried actually implementing the C++ OX concepts paper from like 2008. I tried implementing that a few years ago. And the archetype work that's really expensive. So I think a lot of the Rust compile time pain is based on its generics, getting those earlier type checking errors. But we'll find
Okay,
out.
cool.
Yeah, even if
Well,
yeah.
If anyone, you can do it fast. So, and just last one regarding the Rust. You mentioned that you follow it up closely. I was just wondering, as you were implementing, did you find maybe different alternative pathways would take right now if you started from scratch?
No, I think you mean like how to achieve memory safety. Knowing what I know now, would I do something different?
Yeah, exactly.
No, I think like I implemented the non-lexical lifetimes flavor of borrow checking, which is the current thing that's shipped in the release build of Rust. I think it's good. There's like a kind of a more advanced version that's in development called Polonius, and if that is merged into the release and there's a RFC written, I will totally read that and probably implement that as well. But the Rust flavor of borrow checking is like it's really impressive and it's really robust against adversarial cases. Yeah. All right, let me get to this question on the chat. The string view doesn't use any special syntax. Well, string view has a syntax, right? It's got the lifetime annotations, but they're on the type itself, on the class template. So when you specialize a class template over, narrow character, it gets this lifetime parameter A. And that A is like expressed everywhere, but mostly implicitly. Right. So when you initialize through like a string constant, well, this is going to remain unconstrained, and therefore you can use that string view anywhere. It becomes like static. But if you initialize it on some other slice, it gets the lifetime of that slice. That means like the lifetime of the slice outlives the lifetime of the object on the left hand side. And yeah, you definitely need the annotations. You especially need them inside data members. You can't have a data member that is a lifetime binder that doesn't have a lifetime argument. That's ill-formed. You got to use them, but yeah, if you can rely on these wrappers to make it like less intrusive. I mean, I think about ergonomics, and the C++ ergonomics are fine for most of these types, and you can get by really similar using these safer versions. Can the compiler just see that string views return to static data? No, the other part of the question was on the one where the string view, I think it's str4. Right. Question, I lied this. Like you could, yeah, it could infer in the definition, you could infer that this should be /static because it only uses static constructors or objects that have static lifetime. But that doesn't work because the live analysis is local only. It only considers the definition of the current function. It's not a whole program analysis, and you can't infer lifetimes across the function boundary. So you have to be explicit with lifetimes on the function declaration, right? If I left this off, then this code right here wouldn't know what this lifetime is, and it would complain. It's not going to open up that function and analyze that function. That creates a whole program analysis, and that's where compile times would really get bad. That's when it would really get terrible. So now you have to be explicit on the function boundary, but inside the function, like everything can be done with inference. Like all these types have like tons of placeholder lifetimes that are generated by the compiler. Okay, well, is there a final hand? Because Ben?
Yep, I think I've got the final hand. So yeah, this is all very exciting. A barrier to standardization is that this is a lot of things and a lot of different pieces. So if we were going down the standardization path, we would need to kind of figure out how to break things up into smaller pieces and figure out how to sequence them. So like the tuples and variant stuff, figuring out when to pull those out and what order to standardize things. So that's one thing. But I do still see this as valuable in a large existing code base is a way of like, I'm going to find my data format parsers and I'm going to, make those things safe is, kind of a small bubble of safety that slowly expands outward through the program as I have time to retrofit things. And so, yeah, I even though it'll be a long time, possibly never for, full applications that exist today to go safe, we could still find the stuff that's touching the network or touching the file system, work on those things first and still get a ton of value out of it.
Yeah, I agree. Absolutely. I think it's about finding the, being judicious about what you attack. And I don't have I don't have the answer on how to deal with large source spaces. I mean, I myself don't deal with really large source spaces, just this thing really now. And yeah, I think you can create bubbles of safe code. It doesn't mean 100% safe. It just means like you've reduced your exposure to UB through, using raw pointers or using old containers that don't do bounds checking or whatever. So, all right. Well, thanks a lot. Yeah, I don't know what the next way to like move this forward is, but I think at least like kind of answer the question about, that $1 billion question is like, can you make a superset of C++ that has a safe subset that gives the same guarantees as Rust? And I think that's like absolutely doable. Okay. All right. Thanks, everyone. Oh, does Circle support coroutines? No, I couldn't figure out what coroutines do. I'm sorry. I tried a couple years ago and I need someone to like really baby me through coroutines because it's very complicated. Is there a final hand? Yeah, I can keep going. Who just talk?
final
Just
hand.
yeah. Oh, okay. Um, um, I understand that analysis does not work with. Right. If you want to stay in chat, that's fine. Just turn your mic on so I can hear you. No, it doesn't work similar to the question is can you do like we have return type deduction? Can you do something like lifetime deduction on return type? The answer is no, because lifetimes aren't like that. They're constraints. They're not actual values. It's very odd. But you have to read the LLRFC many times, and then you kind of understand that you're dealing with a different kind of beast, and it doesn't really merge perfectly with the C++ type system. It doesn't merge perfectly with the Rust type system either. It's this completely alien like overlay of constraints, and I mean it works well enough, and it prevents undefined behavior, but it's not something that you can use deduction for. All right, I'll log out. Thanks a lot, everyone.